beta d cos theta plus alpha. Now what I am going to do, I am not alpha, I am going to take 0. Okay, so first what I am going to do, case 1, I do not know what's going to happen. Now I am going to analyze. Let alpha is equal to 0. Okay, that means what? I am not changing them. Already I have took same current. I took same current. I took some phase difference. That could be anything alpha, but that alpha I am making it 0. That means what? What I am doing effectively, for both conductor 1 and conductor 2, I am using simply current I. I am not introducing any phase. That is the meaning of alpha is equal to 0. And again, you know that this is the antenna array axis. Once alpha is equal to 0, you know, again here the phase is 0, phase of the wave to excitation phase is 0. And you know the condition for maximum radiation. When you want to find out the maximum direction of radiation, simply that is psi is equal to psi has to be 0. Once if psi is 0, you calculate the remaining thing, beta d cos theta plus alpha. What is alpha? Alpha is equal to 0. Then from this, beta d cos theta is equal to 0. Anyway, beta d is some realistic quantity that cannot be 0. So simply cos theta is equal to 0. That means what? Theta is equal to cos theta is equal to 0 only when theta is equal to pi by 2. Theta is equal to pi by 2. Then you know from the discussion of theta, where you have taken your theta like this. Then you think of once if theta goes to pi by 2, what is your observation point? Once if theta goes to pi by 2, then once if theta is pi by 2 means what? This is your observation point. You are here. If you are here, then only your angle from this will be pi by 2. Then only the angle will be pi by 2. Then what is happening? When you choose alpha is equal to 0, and if you are exciting the two antennas with the same current without any phase difference, then your maximum radiation is perpendicular to the array axis. What is happening? So because this is giving the direction of maximum radiation, this is what? The direction of maximum radiation. Because why this is giving you the direction of maximum radiation? Because the condition you have taken like that. Because when you make psi is equal to 0, indirectly that will give you the direction of maximum radiation. So this is the direction of maximum radiation. Okay, maximum radiation. So that means what? Theta is equal to pi by 2 is the maximum radiation. When you are getting when you are having maximum radiation perpendicular to the array axis, that particular condition is called broadside array. That particular this is called broadside array. This is called broadside array. Broadside array means what, sir? The direction of maximum radiation. This is called broadside array. The direction of maximum radiation will be perpendicular to the array axis. Okay, array axis. So now I will simply conclude broadside array. What is broadside array? Broadside array, in a 2-element antenna array, current is same and no phase difference. If current is same and no phase difference, then the direction of maximum radiation, will be perpendicular to array axis. This array axis is very, very important. What is broadside array? If your direction of maximum radiation is perpendicular to the direction of maximum radiation is perpendicular to the array axis, then that condition is called broadside array. There, what is true? Current is same, no phase difference. Okay, current is same, current same, and no phase difference. Very important. So when you have two antenna arrays, if you are feeding with the same current for both antenna, you are not changing the excitation phase. That is alpha is equal to 0. But you cannot have a control over this one, because you can have control on the excitation phase. You cannot have a control here because that will be introduced, because definitely the delay will be there between these two waves. Then definitely this portion will be introduced. Okay, somehow it is giving you some other condition. Okay, so you can have a control over only excitation phase. Okay, you cannot make other phase as 0. This and all you cannot make as a 0. That may become anything depending on the other condition. So when excitation phase is 0 and if it is having same current, then finally your direction of maximum radiation is perpendicular to the array axis. That particular array is called as broadside array. That particular array is called as broadside array. Okay. Now next one is broadside array. Then when you have a broadside array, what is the direction of radiation pattern? Okay, you are at broadside array. Say this is the okay, and you can imagine this as a isotropic radiator or this as a conductor which is going inside the screen and conductor which is going inside the screen. Then whenever you have an isotropic radiator or conductor which is going inside the screen, in case of broadside array, you are having maximum radiation perpendicular to the array axis. Okay. Now, if I have chosen a point here, I will get the direction of maximum radiation here, or otherwise, I can also choose a point here because that is also perpendicular to the array axis. I can also choose the point here. So I can have a radiation pattern like this. Okay, so in this process, what is happening when you have a radiation pattern like this? When you take n element array and all, in future instead of 2 element array, we used to take n element array. Then finally you will get some main lobe as well as the side lobe. These are all called side lobes. This is main lobes, main lobe. This is side lobes. Okay, the power is available both in main lobe as well as some part of the power is available in the side lobe. But side lobe is not used for radiation purpose because that will not go to longer distance. So some power is wasted in the side lobe. So effectively, if you want effective communication, you have to try to eliminate the side lobe to have a effective communication. Okay, you have to try to eliminate the side lobes. Try to eliminate the side lobe to have a effective communication. Try to, in general, try to, but yeah, there is no other way to go. Definitely some side lobes will be there. Try to eliminate side lobe to have effective communication. Effective communication means your aim is to concentrate the power only on the main lobe. Try to eliminate the side lobes to have effective communication. So this is simple example for broadside array, n element broadside array actually. So once we have calculated for 2 element array, that can be extended for n element array also. We are not going in detail. Okay, so let it be 2 element or n element, always the direction of maximum radiation is perpendicular to array axis. Then this is called beam width between the first null. Okay, this is the main beam width. As I go, this is my main beam width. This is my direction of maximum radiation. When I go from here, I am getting first nulls here. First nulls. Okay, this is my first null. Okay, when I go there like this, I am getting nulls. This is called beam width between the first null. Because once if I go there, I am getting another nulls. But that is not the nulls created from the main lobe. That's the null created from the side lobe. That's why the first null is called beam width between the first null. That means what? You stand in the direction of maximum radiation. You move either this side or this side. Definitely you will find a null. That null is called as beam width between the first null. Okay, so this is the beam width between the first null. These are all second null, third nulls like that. And again, if you do here also, that is also beam width for this beam. This is the beam width between the first null. Okay, this is the null between the side lobes. Okay, and again, please always remember, generally you'll get nulls between two maxima. Okay, once if you have two maxima, see, in some cases, if you are not having side lobes, okay, if you are not, assume that you are not having side lobes, and here maxima is there, and again here also maxima is there. Definitely between the two maxima, definitely at least one null has to be there. That's another idea. So if you are not having side lobes and all, between the two maximas, definitely there should be one minimum, one nulls has to be there. That's some properties of radiation pattern of array antennas. Okay, once if you go in detail, then you'll know all these things. Okay, so broadside array. So what is the condition for broadside array? Finally, broadside array radiate perpendicular to the direction of array axis. Okay, the maximum radiation is perpendicular to the array axis. The finally one more thing you have to remember. What is the beam width between the first null? This beam width, very important exam point of view, just remember. Okay, very rarely they used to ask this question. Beam width between the first null is equal to 114.6 degree, 0.6 degree divided by L by lambda. L means length of the array. Okay, length, total length. Okay, this is L means what? Length of the array. Length of array. Very precisely, the length of the array is n minus 1 into d. If n is large, you can write it as nd. Okay, this is length of the array. Okay, see, because d is the distance between the array. If you have n element, you will get n minus 1 spacings. So n minus 1 d is the length of the array axis. Then you can approximately, if number of array is I, n is I, then you can take it as nd also. So, and again, this is the formula for beam width between the first null in case of what? Broadside array. In case of what? Broadside array. So next one is end fire array. So next one is end fire array. So somebody tell me, this is the only direction, the maximum radiation. Is rendu mattumdana, upward here and here, or is there any other direction? So inga vandu neenga imagine pananum. This is your line. For this array axis, how many perpendicular will be there? இது வந்து array axis சார். இந்த array axis க்கு எத்தனை perpendicular வர முடியும்? இப்படி போனாலும் perpendicular, இப்படி வந்தாலும் என்னது? Perpendicular. இப்ப suppose நான் இங்க இருந்து அப்படியே ஸ்கிரீனுக்கு வெளியில வந்தாலும் perpendicular தானே? If I am here, if I come out of the screen, that is also perpendicular. If I am here, I am going into the screen, that is also perpendicular. That means what? Actually, we are drawing only 2D. You rotate this diagram in this manner. Okay, you rotate this diagram in this manner. Okay, what I'm telling, you rotate the diagram inside the screen and come up from the bottom of the screen. You rotate the diagram in this way. All are radiation pattern of that particular antenna. That is the original 3D radiation pattern of the antenna arrays. அது புரியுதா சார் நான் என்ன சொல்றேன்னு? Yes, anybody? என்ன சொல்ல வரேன்னா, இப்படி இருந்தா இது மட்டும் தான் பெர்பெண்டிகுலர் கிடையாது. I can also draw a line here also perpendicular like this. I can also draw the line like this. I can also draw the line like this. But what is important? This is the antenna array axis. My direction of maximum radiation will be perpendicular to the array axis, but that can be anywhere, like a circle. இந்த கான்செப்ட் புரியுதா? Anyone? புரியுதா புரியல ஏதாவது ஒன்று சொல்லுங்க.
Okay sir.
Okay, not properly understood. What about others?
Yes sir, புரியுது sir. அது சுத்தி அப்படியே
yes, rotational manner you have to do, because perpendicular na இப்படியும் வரலாம் towards you வரலாம், that may go away from you also. Okay, so that means you are getting entire 360 direction like that. Okay, in a like a circular manner. Yes sir.
Antennas எல்லாமே நம்ம 1 by 1 வச்சிருக்கோம். 360 டிகிரி சொல்றீங்க, ஒரு டைரக்ஷன் எப்படி இருந்தாலும் அட்டென்யூட் ஆகும்ல?
புரியல என்ன சொல்றீங்க?
ஆண்டனா அரேஸ் தானே சார் சொல்றீங்க?
ஆமா,
எல்லாமே 1 by 1 அரேஞ்ச் பண்ணிருப்பீங்க. இப்போ ஒரு டைரக்ஷன்ல மட்டும் ரேடியேஷன் வந்து குறைஞ்சிருக்கும்ல சார்? 360 டிகிரியும் கிடைக்கும்.
இப்போ I have one doubt. இதை ஃபர்ஸ்ட் சொல்லுங்க. If I have antenna like this, இது போல radiation pattern horizontal planeல கிடைக்க சான்ஸ் இருக்கா? சான்ஸ் இருக்கு தானே? If I have antenna like this horizontal planeல அது சான்ஸ் இருக்குங்களா? When I have antenna like this horizontal planeல எங்க போனாலும் நமக்கு radiation கிடைக்க சான்ஸ் இருக்கு தானே? You stand here, that is also perpendicular 90 degree. You stand here, that is also perpendicular, that is also perpendicular 90 degree. அதே கான்செப்ட் தான் நான் அங்கேயும் யூஸ் பண்றேன். You stand any see, அங்க வந்து நீங்க கொஞ்சம் இப்போ அதாவது நான் என்ன பண்ணேன், எல்லா ஆண்டனாவும் going inside the screen. இப்போ இது எல்லாத்தையும் ஒண்ணாக்கிட்டா இதுவே ஒரு கண்டக்டர் மாதிரி தானே? If I bring all antenna closer to each other, இதுவே வந்து ஒரு லைன் மாதிரி தானே? It is going inside the screen. Then finally, what is the see, the line is going inside the screen. Then what is the perpendicular to this line? I can stand here. Here also that is perpendicular to the, because line is going inside. This is also 90 degree. I can stand here. That is also 90 degree because line is going inside. Even if I stand here, that is also 90 degree. So na enga ponalum, the rotation manner you will get the same power because line is going inside the screen. Line is going inside the screen. Please imagine here I am putting dot means you have to imagine either this as isotropic radiator or otherwise you have to imagine that the line antenna array is really going inside the screen. I am showing only dot. Okay, see the antenna is really going inside the screen, something like this. It is going inside the screen. Antenna length is going inside the screen. We are seeing only this portion here. இது புரியுதா சார் உங்களுக்கு? This is my antenna, physical antenna. I am placing like this. Only I am seeing the front portion. Then you imagine what is the possibility where you will get the power, like that you imagine. Okay, or otherwise you simply imagine as a isotropic radiator. Okay, for again one more thing sir, if you அதாவது உங்களால imagine பண்ண முடியல, no problem, you simply remember the formulas. That's important finally exam point out. Okay, because you will take some time actually because antenna itself is a different subject, and again I am just rushing up because we cannot spend much time here because this consists of 4-5 subjects electromagnetics. Okay, because antenna is a different subject, wave propagation is a different subject, microwave is a different subject, transmission line and waveguide is a different subject, EMT is a different subject. Around 5 subjects is there we are discussing. That's the main problem. So try to understand and later you refer the books. And again, even if you don't understand, no problem, simply remember the formulas. Yes. Okay, so next you'll go for end fire array. Okay, finally what is important, this formula you have to remember because I want to make some conclusion between broadside array and end fire array. That's why I am asking you to make some visualization. Okay, because I am drawing it here 2D, but this is actually 3D. Okay, upward as well as the downward 3D. So now I'll go to the end fire array. Okay, I'll complete around 6:30. Okay, next one is end fire